for the next talk, Russ will tell us about Type-Outference. All right.
Hi, I'm Russ Tate, and I'm excited to be presenting this work I've been doing with the Kotlin team in order to make their type system decidable. The team views decidability as not just an academic principle, but it's something that can provide real pragmatic value for them. In particular, they see it as a means for providing a reliable and stable programming language that has a declaratively specified standard that's easy to extend with oft-requested features. And the work I'm going to present today seems to lay the foundations for making this possible. Now, you might think that decidability is difficult because Kotlin is a large language. But in fact, decidability for even just core object-oriented features has been an open problem for decades. For example, consider this simple program. Now, it is the case that algorithms by both Kotlin and from the literature can validate this program. However, if I make this change, then that's no longer the case. And to see what goes wrong, we can look at what happens with Kotlin. So with Kotlin, this loop variable, it infers its type to be foo any because that's the principal type of its initializing expression. However, that causes this later assignment to get rejected because the foo of any returned by bar is not a subtype of foo any because foo is contravariant rather than covariant. As for algorithms in the literature, this program is simply out of their scope because this interface is irregularly recursive. That means that the types in the program cannot be represented structurally using just a finite graph, which these algorithms rely on in order to ensure termination. Now, you might be looking at this interface and thinking, this doesn't look very realistic. Maybe this isn't a problem in practice. But let's take a look at some examples of method signatures taken from standard libraries across industry languages. Here are examples from Kotlin, Java, C#, and Scala. All these examples are generic, and many are furthermore irregularly recursive. And this is problematic because both these features by themselves are known to make subtyping undecidable with structural types. And while in this paper I only show how to address irregular recursion, the point is that we can't rely on structural techniques alone to solve this problem. We need a fundamental new insight in order to scale to the expressiveness used in industry. So going back to our program, notice that our interface has a name. In Kotlin, this name is significant. That is, even if two differently named interfaces have the exact same structure, Kotlin will still view their types to be distinct. That means that Kotlin generics are nominal. And one of the key contributions of the paper is to provide an algorithmic technique for taking advantage of nominality. To illustrate it, I'm going to walk through how we validate this program where others cannot. And for that, I'm going to rearrange and space out the program to make a simpler, easier visual. So the first challenge is the fact that this loop variable has no type annotation. And we're going to address that challenge the same way many others do. We're going to introduce a type variable L to represent its type. And here I put a little circle over it to indicate that it's a hole in the program that we have to deal with. The second challenge is this bar invocation. We have to resolve this bar. And what Kotlin does is it resolves it based on the preliminary best guess of the receiver's type, which in this case is foo any, and that's overly precise, causing the problem to get incorrectly rejected. Whereas what algorithms from the literature do is they turn this into a structural constraint, and that turns out to be too relaxed, causing them to fail to terminate on this program. So what we do is we introduce an event-driven technique. We install what we call a label listener. This listens to the type of the receiver L. More precisely, it's going to listen to changes in information about the label of that type, such as the name of the interface that it belongs to. And as it learns information, it's going to dynamically generate constraints that reflect how that information affects the validation of this indication, which I'll illustrate later. With that label listener installed, we then move on to standard constraint collection. So for example, here we have foo any. That's the type of init that flows into loop. And as such, we know that foo any needs to be a subtype of L. Now, we could go on, but for the sake of illustration, I'm going to jump into illustrating what effect this constraint has on our algorithm. In particular, from this constraint, we know that the label of L is at most foo. That's new information that we just learned, and as a consequence, our label listener triggers and reacts to that. in particular because now we have enough information to resolve the bar method. Knowing just about that label, we now know that this bar method has to be resolved using this signature from the foo interface. And so the label listener will then generate constraints to validate against that specific signature. Now, the first thing it has to do is say, okay, well, the receiver needs to be valid, so loop needs to be a foo, but we don't necessarily know what it has to be foo of. But label listeners are allowed to introduce more type variables, and so it'll just introduce an A and say that L needs to be a subtype of foo of A for some A. It can then reuse that for validating the rest of the method. So in particular, this argument is valid if L is a subtype, or A is a subtype of L, other way around. And the result is assignable to our loop variable if foo of A is a subtype of L. And at this point, there are no more direct flows we have to capture as constraints, and we've extracted what we call the graphical core of the program. Now, in reality, the graphical core of the program contains that label listener, and I've just sort of partially processed it for the sake of providing a simpler visual. In general, graphical cores can contain unactivated label listeners that are allowed to dynamically generate more type variables, constraints, and even more label listeners, so long as they do so in a well-founded manner. Thus, graphical cores provide a means for extending traditional techniques with label listeners as a way to dynamically react to nominal information. But at this point, we've extracted sort of the essence of the validity of this program, and so we can throw the program away and just reason about this graphical core. Traditionally, we would do so in the context of type inferability, where the key question would be, is there some solution for L and A that satisfies these constraints? And I'm going to jump ahead a bit and say, well, there are existing algorithms already that can solve these constraints and to give you that this is a solution for L and A. Now, these are complicated types, but there also are existing solutions for often being able to reduce types to sort of more compact recursive types. But this is still problematic for us because Kotlin doesn't have recursive types. Now, we could, of course, always extend Kotlin with recursive types, but we found that even if we do this just behind the scenes, it still causes problems for users, for the compiler, and especially for our proofs. Nonetheless, this program is safe, so we would like to be able to accept it. This prompted us to look into whether there's some other notion of program validity besides type inference that wouldn't require these convoluted types in order to accept this program. For that, we explored a new perspective. We said, rather than viewing L and A as unsolved types, what if we thought of them as abstract types? And these collective constraints are simply the assumed subtyping properties for these abstract types. Well, then I've just defined a custom type system where my program type checks. So which seems great. But on the other hand, I've just defined a new type system. So how do I know this type system is safe to use? And that's where the rest of the algorithm comes in. Rather than exploring, is there a solution for L and A, it's exploring, is this a safe type system to use for my program? And already the constraints sort of capture the direct flows in the program, and we can see there's nothing like obviously wrong, like an integer flowing into string. But they also enable a bunch of indirect flows, or imply a bunch of indirect flows, and we have to consider those as well. So we're going to analyze these constraints in much the same way that other existing algorithms do, but with a different perspective on what these steps is going to mean. For example, here I have foo of any flowing into L, and I have L flowing into foo of A. So I have this indirect flow, and I need to know that foo of any is a subtype of foo of A to know this indirect flow is necessarily safe. However, that's not true with the constraints I've collected. But this program will still type check even if I add more constraints to this system. So I could add that A is a subtype of foo of any, which at least locally seems perfectly safe to have. And now we have the required subtyping. And I can do this for more indirect flows in the program. Here, learning that A needs to be a subtype of foo of A. And here, learning that foo of A needs to be a subtype of A. And then here, I learned that foo of A needs to be a subtype of A. Oh, but in that last case, I already know that. That's already present in my constraint system. And I've reached a state wherein all the subtypings required for these indirect flows are in fact implied by the constraints I've derived. As such, we call this graphical core consistent. And if we reflect on this process, notice that in every step where I derived a constraint, I always derived constraints between types that were already present in our collected constraints. That puts a finite cap on this set of constraints I can derive, which ensures this process terminates. Even if I add label listeners that can dynamically generate more types and constraints, they are sensitive to only label information and as such can only fire a finite number of times, still ensuring termination for this process. This means that graphical core consistency is decidable. Furthermore, because I've reached a state where all the required subtypings are implied by the constraints, I was able to show that this means this type system, custom type system, is safe to use. This prompted us to define this concept of type consistency, wherein a program is valid if it can type check within some consistent type space. Type-inferability then is just a way to establish type consistency where you're using a predetermined consistent type space. On the other hand, type consistency does not ensure type-inferability, so we can't call our algorithm the type-inference algorithm. So as a pun on the fact that our algorithm works by sort of factoring these type variables out of the constraints, we call decision procedures for type consistency type-outference algorithms, and introducing sort of a generalization of type inference. Now, I recognize that this is kind of weird and far-fetched, so I formalized and mechanized all of this in Rocq to establish confidence in these results. I proved that type consistency does indeed ensure progress and preservation, even if we don't get a solution for the constraints. I proved that user-expressible types form a consistent type space, which means that any program that is inferable using user types is valid according to type consistency. I proved that graphical core consistency is decidable even with these label listeners able to dynamically generate more types or variables, constraints, and even label listeners. And I proved that I combined that with that process for extracting a graphical core from a program to prove that type consistency for programs is decidable. All this can be found in our reusable and reproduced artifact that's available online through the ACM digital library. So now, hopefully that explains the title of this paper. This is a foundations paper because it focuses on just core object-oriented features. It achieves decidability by using event-driven label listeners as a way to dynamically react to the nominal information present in many object-oriented languages. And it introduces type consistency as a more relaxed but still safe notion of program validity, sort of replacing or extending the concept of inference to outference. As I mentioned in the beginning, this is sort of a first step in our work. So if you're interested in how we've extended these concepts to the much larger Kotlin language and extensions we're building thereupon, feel free to come, or please come find me afterwards. Thanks very much, everyone, for your attention, and I don't know if there's any time for questions.
All right, thank you. Questions? Yes.
Hi, Ross. I was curious, you're doing this in the setting of Kotlin, which in addition to having all the things you showed, also has overloading. Does that wind up complicating the story at all?
Yeah, so overloading is, in some ways, it complicates it in that, yes, overloading just makes things necessarily messy in provably hard ways. The other way, it makes things messy in a way that we can't really improve upon, so you can kind of plug and play a overloading semantics, and it has the obvious interplay with these kinds of features. This what I've presented so far is polynomial time, whereas overloading provably makes it not polynomial time. But our goal is that essentially if you have a system where overloading is well designed, they've made libraries that have these nice behaviors, it'll always still perform polynomial time and have good semantic guarantees. Oh, yeah, sorry.
We still have time for one quick question, if you want. There was another question. Okay.